This is Vibhav. Welcome back to my channel. So in this video, I wanted to talk about the paradoxes. So basically what a paradox is it's a self-contradictory statement. So when I say a bulb is turned on, and I also can say that the bulb is turned off, it's a paradox, right? Because the two statements essentially contradict themselves. In fact, there's a paradox based on this certain kind of a bulb that is on and off at the same time, or rather, we can't determine whether it's on or off at a given time. So that's about an introduction to paradoxes. So there are two main paradoxes that I would like to talk about, and one of them is actually very simple to understand in essence, and that's Galileo's paradox. So what Galileo thought of was we have a lot of natural numbers. We have an infinite number of natural numbers. We have 1, 2, 3, 4, 5, 6, and etc. And we also have these specific natural numbers which are given the privilege of being a perfect square. So 1 is a perfect square, 9 is a perfect square, but 8 is not a perfect square, and so on. So there are two ways of thinking of this. The first way is, since not every natural number is a perfect square, the total number of natural numbers must be much more than the total number of perfect squares. This seems quite logical, right? However, when we come to the second way of thinking of it, which is that if there is a certain number, let's say we take 27 and we square it, we get 729. When we square 31, we get 961. We square all sorts of numbers that we get and we get a new natural number. So this essentially means that there's a one-to-one correspondence between a natural number and its perfect square. So that also should mean that the number of natural numbers is equal to the number of perfect square natural numbers. Well. So this is indeed a paradox. So what Galileo decided was that these infinite sets, such as the set of natural numbers or the set of perfect square natural numbers, couldn't exactly be compared the way we compared all these finite sets. So he put it at that. However, a couple of centuries later, I'm not sure, uh, Cantor came along and he came with an excellent method to talk about all these infinite sets, which I'll be talking about in a later video. Okay, now we move on to the second paradox. This is quite a deeper one. So this is also about sets. It's in fact about a certain kind of set. So if you just read what the paradox says without actually thinking about what you're reading about, it sounds like a bit of nonsense. But once you start thinking about it, so it sounds actually like a very fascinating thing. So, and it is obviously very fascinating. And so here's how the paradox is. Suppose we have a set that is the set of all sets that do not contain themselves. So I guess I need to give an example. Okay, so among the two examples I've given, the first set is set of 1, comma 2, which obviously doesn't contain itself. But on the other hand, the second set I've given is a set of 1, comma, set of 1, comma, set of 1. It's an infinitely proceeding. This set can be defined with an infinite function, I believe, but this, if you look at the second element of the set, or if you look at the second element of the second element of the set, it's essentially the same as the set. So when if the set S, if you call the set as set to be S, S is nothing but set of 1, comma S. So this is a set that contains itself as one of its elements. So this set A would be part of the set we were talking about, which is a set of all sets which do not contain themselves, which is nothing, also known as the Russell set in certain cases. I mean, it's not the exact formal name given to it, but you can also refer to it as Russell set, and that's what we will be doing. So set A is present in the Russell set, but set S is not present in Russell set. So is Russell set present in itself? And that's the paradox. So suppose we say Russell set is not present in itself. It means, okay, so suppose Russell set doesn't contain itself. It means it doesn't contain a set which is a set of all elements that do not contain itself. So To think about this more exactly, we'll go back to how we define the Russell set. It's the set of all sets that do not contain themselves. So basically, if we have a set P, the set if the set P contains the set P as one of its elements, it means it should not be present in set R, which is nothing but Russell's set. So if I say set R doesn't contain itself, it essentially means set R should be in the Russell set, which means it should contain itself. I hope that was clear. And suppose I say that set R contains itself, if I look at it from the other direction and say, okay, let me say the Russell set contains itself. It means that it contains a set which contains itself, which means it's not defined, it means it's not the Russell set exactly. And this is basically the most famous paradox ever, and this is personally my favorite paradoxes-1. So as you can see, I was actually pausing mid-video a lot while doing this because paradoxes are things that you should think about. Even when you're saying something and when you suddenly think of a paradox, you should stop saying something and then you should think about it a little more, try to get a clearer picture, try to get a bit more confused, which is what will actually happen in most cases. And then the beauty of paradoxes is you never have a perfect answer. It's vague and it's something which mystery lovers will actually love.